Hello, I am Antonio Cruciani from Aalto University, and today I'm going to present fast percolation centrality approximation with importance sampling. This is a joint work with Leonardo Pellegrina from the University of Padua. In this work, we are given a graph in which each node is associated with a percolation state that is a real value between 0 and 1, and we want to compute the percolation centrality of each node in the network. The percolation centrality of a node V measures its importance as the weighted fraction of shortest path that are traversing it, where the weights depends on the difference between the percolation state of the source node and the target nodes of this shortest path. A typical application of the percolation centrality is to identify key nodes for the diffusion of an infection in the network, where the percolation states represent the level of infection of each node. Formally, the percolation centrality of a node V is defined as the summation of all the distinct couples of nodes S and T of the ratio between the number of shortest paths between S and T passing through the node V over the number of shortest paths between S and T times this function kappa here, that is proportional to the difference of the percolation state of the source node minus the percolation state of the target node, where the function kappa of S of T of V is equal to the ratio between the ramp function of the difference between the percolation state of the source node minus the percolation state of the target node over the difference among all the distinct couple of nodes of the percolation states. If you want to compute the exact percolation centrality of each node in the network, we will need time at least n squared, and this becomes quickly impractical in real-world networks. Our goal instead is to compute an approximation of the percolation centrality for each node in the network, and formally is defined as follows. Given an epsilon value that is between 0 and 1, and you can see this epsilon as an accuracy parameter, we want to compute an epsilon approximation for each node in the network. An epsilon approximation of the percolation centrality is defined as a p tilde of v for each node v in the network, such that the error of the approximation is at most epsilon for each node in the network. The state-of-the-art method to estimate the percolation centrality was proposed by Delima et al. In KT 2020. They used uniform sampling to approximate a doubly normalized version of the percolation centrality with an additional 1 over n squared factor. They also showed how to generalize the results for the Bedouin centrality estimation to the percolation centrality estimation problem. And they showed that in order to achieve an epsilon approximation of this doubly normalized version of the percolation centrality, we need to get a sample size that depends on the logarithm of the vertex diameter of the given graph. However, there are some issues with the state of the art. Indeed, Delima et al. Approximated a doubly normalized version of the percolation centrality, and in this case, the percolation centrality of each node is between 0 and 1 over n squared. This means that if we set our epsilon to be at least 1 over n squared, our epsilon approximation is going to be uninformative, and in this case, it is better to directly output 0 for each node in the network. While if we set our epsilon to be strictly less than 1 over n squared, we will need at least n to the fourth samples to approximate the percolation centrality up to this epsilon error. But to do so, we will need much more time than running the exact algorithm of the network. So we can conclude that no truly effective algorithm exists to approximate the percolation centrality. But why do we use importance sampling instead of uniform sampling? A key observation when computing the percolation centrality is as follows. Given a source node S and a target node T, such that the percolation state of S is at most the percolation of T, you will have that the function kappa of S of T of V is going to be always equal to 0 for each node V in the network. So this, in other words, means that sampling S and T that have this property on the percolation state is basically useless. Now that we have this observation, we can build arbitrary bad instances for the uniform sampling. Indeed, if you observe this toy example here, in which only two nodes have a percolation state that is greater than 0, you will observe that using uniform sampling, you will need a big sample size in order to pick the red node or the light red node as a source nodes. While if we use importance sampling, we can boost the probability of picking these two nodes as source nodes for computing the percolation centrality. Moreover, using uniform sampling, we have high variance in our estimates, while with importance sampling, we lower the variance of the estimates. And here we propose a new algorithm called purchase that is based on importance sampling, that returns an epsilon approximation with probability at least 1 minus delta efficiently. And this happens thanks to new sharp sample size bounds. The high-level idea of our algorithm is to use importance sampling to prioritize a couple of nodes S&T that contribute more to the approximation of the percolation centrality. As said before, we will use importance sampling to approximate the percolation centrality. What actually we want to approximate is an expectation of a function f of x given a probability distribution p, from which it might be inefficient to sample. And instead of sampling from p, we sample from an importance distribution q, which emphasizes important regions that we would like to sample. And we have the constraint that the expected value of the function f of x given p must be equal to the expected value of the function f of x times the ratio between p of x and q of x given the distribution q. A key parameter to study when designing important distributions is the maximum likelihood ratio d hat, where the maximum likelihood ratio d hat is equal to the maximum over all the point x on which we can evaluate the distribution q of the ratio between p of x over q of x. And when d hat is approximately 1 or close to 1, we have a low distortion, and this allows for very good estimates. We are now ready to describe purchase, and we are going to start by describing the importance sampling distribution. The idea is we want to sample two couple of nodes S and T with probability kappa of S of T of V. Now the challenge is that we want to estimate n averages, so the set of P of V for each node V, simultaneously. But the weights kappa of S of T of V depend on V itself. Instead, we define another function, kappa tilde, that is defined over all the couple of nodes in the network, that resembles a bit the function kappa, but has no dependency on the node V. And kappa tilde is equal to the ratio between the ramp function of the difference of the percolation state of the node S minus the percolation state of a node T over the summation over all the distinct couples of nodes in the graph of the ramp function of the difference of the percolation states. And for any shortest path, tau st between two nodes S and T, we define the importance distribution Q as Q of tau of st equal to be the ratio between kappa tilde of S of T over the number of shortest paths between S and T. And this, we define it for every shortest path in the given graph G. Now that we define the importance sampling distribution, we have to describe how to sample from this distribution. And our problem now is as follows. We want to sample two nodes S and T with probability kappa tilde of S of T. To do so, we use the following two-step approach. We first sample S, the node S, with the following marginal, and then we sample the node T condition to the fact that we sample the node S. Once we sample both nodes, we perform a bidirectional balance BFS from both S and T. And once this BFS has been both BFS touched and so terminated, we basically computed all the shortest path between S and T. We pick a shortest path, tau st, uniformly random among all the possible shortest path between S and T. If done naively, the first two steps of this sampling procedure will require linear time in the number of nodes for each sample that you want to draw from this distribution kappa tilde of S of T. However, in our paper we show that this can be done very efficiently in log n time. And more formally, we show that purchase correctly draws L samples from the importance distribution Q in time big O of n plus the number of samples L times log n, so the time needed to sample from the distribution kappa tilde of S of T, plus the time needed to perform the bidirectional balance BFS from S and T, and linear space in the number of nodes and edges of the graph. Now that we defined how to efficiently sample from our importance sampling distribution, we describe how to update the percolation centrality estimates of the nodes in the network. Every time that we sample a shortest path from the graph using the importance sampling distribution Q, we update the the percolation centrality scores of the internal nodes of the shortest path by the ratio kappa of s of t v over kappa tilde of s of t. In this specific example, once we sample the shortest path between s and t, we will update the scores of b by kappa of s of t of b over kappa tilde of s of t, and the score of c by kappa of s of t of c over kappa tilde of s of t. We proved that our estimator is unbiased, and we proved an upper bound of the variance for the estimates of each node v. Indeed, we showed that the variance of the estimates of a node v is upper bounded by the maximum likelihood d hat of the importance distribution times the percolation centrality of a node v. Since we are talking about sampling, we need to understand how many samples we need to draw from the distribution in order to achieve the desired epsilon approximation. In our paper, we provide a new data-dependent upper bound of the sample size. Our sample size depends on three key parameters: v hat, that is a bound to the maximum empirical variance, and d hat, that is the maximum likelihood ratio of the importance distribution that we consider, and rho hat, that is a bound to the average path length. Now we observe that the average path length is at most the diameter of the graph, and in real-world networks, the diameter of the graph is much bigger than the average path length. And most importantly, we have that all these quantities can be estimated efficiently. And in our paper, we show how to obtain sharp bounds for all these quantities. As a next step, we show strong lower bounds for the uniform distribution, and to do so, we define this parameter delta here called the state gap. And we show that when the state gap is omega of 1, you have that the likelihood ratio of our importance distribution is constant. While we show that there exist instances for which delta is in omega of 1, for which the likelihood ratio of a uniform distribution is omega of n. And finally, we show that there exist instances with still delta in omega of 1, where we need omega of n squared random samples from uniform, while we need big O of n random samples for purchase. And this is a factor of n improvement compared to the uniform distribution. Moreover, in all the real-world graphs analyzed in this paper, we observe that our delta is equal to 1. We tested uniform and purchase on different real-world networks, and since it's difficult to find real-world networks with percolation states assigned to the nodes, we assign percolation states to the nodes of these real-world networks using different settings. We define four main settings. The first one is random seed, and in this setting we selected a constant number of random nodes in the network, and we set their percolation state equal to 1, and for the rest we set the percolation state equal to 0. As a second setting, we defined a random seed spread, in which we selected log n random nodes, and we simulated an infection spreading process starting from these nodes. Then we defined the isolated component setting, in which, given a graph G from the list of the considered graphs, we set the percolation states of the nodes of the graph equal to 0. Then we added a constant sized component that is disconnected from the original graph, but connected within the component, in which half of the nodes have percolation state equal to 0, and the remaining nodes have a percolation state that is greater than 0. This is meant to be a sort of stress test for our sampling algorithms, because it's going to be difficult to pick nodes from this small component. And finally, we used the approach used by De Lima et al. In their experiments, in which for each node in the network we assigned a uniform value between 0 and 1 as a percolation state to that node. As a first experiment, we show the performances of the uniform sampling as an epsilon approximation algorithm. We ran the uniform sampling using different values of epsilon and using the upper bound of the sample size proposed by Lima et al. And from these plots, we observe that uniform does not provide accurate estimations of the percolation centrality. Indeed, the maximum error obtained running the uniform sampling algorithm is always above the prescribed epsilon value. Next, we show the performances of purchase versus uniform in terms of maximum absolute error. And here, for these experiments, we use a fixed sample size that varies between 10 to the third to 10 to the sixth. And on the x-axis, we show the maximum absolute error for purchase, and on the y-axis, we show the maximum absolute error for the uniform sampling approach. We observe that the uniform sampling is always worse than purchase, and moreover, we observe that purchase provides up to 2 orders of magnitude improvement compared to uniform. And this also shows that purchase is significantly outperform uniform on every graph and every setting. In this experiment, we compared the two methods, not using a fixed sample size, but increasing the sample size until the error becomes lower than a given epsilon. From the two plots, we can see that purchase converges using a much less sample size than uniform, with orders of magnitude improvements. This also confirms that uniform has a much higher estimation variance. More importantly, we observe that in several cases, uniform does not conclude after a reasonable amount of samples. Indeed, we set a maximum cap on to 10 to the 8, failing entirely to obtain accurate approximations in a reasonable time. We compared the running times of the two approaches using a fixed sample size that varies between 10 to the third to 10 to the sixth. We observed that purchase and uniform have comparable running times. Moreover, we observed that the important sampler running time is negligible compared to the one of the BFS traversal. So this suggests and confirms that our sampling approach is very fast and efficient. As a last experiment, we show that running the between centrality and ignoring the percolation states of real-world networks, for which we have ground truth percolation states, leads to significantly different results compared to using the percolation centrality that takes into account these percolation states on these real-world networks. Indeed, we used two types of real-world networks. We used opinion networks and harmful content networks. In the first one, we have that the percolation states have value that can be either 1 or 0, representing the different opinion that a node can have. And in the second one, we have that the percolation state is a real value between 0 and 1 and indicates how dangerous is that node for the network. For these networks, we observe that the scores of the nodes computed using the percolation centrality and the between centrality are significantly different. Moreover, it's not only about the scores, but also about the rankings. Indeed, the most central nodes using these two different centrality measures are strikingly different. And this suggests that we have an advantage in using the percolation centrality instead of a between centrality in this kind of networks. In conclusion, we presented purchase, a novel approximation algorithm for the percolation centrality. We defined a novel important sampling distribution from this problem. We provided tight theoretical guarantees for our algorithm. And finally, we showed that purchase consistently outperformed the state of the art, theoretically and experimentally. Thank you.